So here are some problems from section 2-3. Let's start with problem number 8. Find the points of continuity and the points of discontinuity for the function. And function number, the problem number 8 is the function cotangent of x. So this is where I'm heavily dependent on your training in your pre-calculus class that you absolutely should know what your trigonometric functions look like. So if I remember cotangent, I believe it has asymptotes at 0, at pi, at 2 pi, negative pi. It is not defined. It has vertical asymptotes wherever sine is 0, because cotangent is cosine over sine. If I remember correctly, in the first quadrant, where x values are between 0 and pi over 2, it's positive and asymptotic. Where cosine is 0 and pi over 2 it crosses, and then from pi over 2 to pi, it's negative. And then we repeat that pattern. And that's a reasonable guess at how cotangent looks. Discuss its discontinuities. Discontinuous, see, negative pi, 0, pi, 2 pi. Can we write an expression that captures all those ideas? I'm going to say it's discontinuous at n pi, where n is an integer. I may say it's continuous on the intervals, and they're open intervals, from n pi to n plus 1 pi. So if you took any value n, it would create an interval, and it would be continuous inside there, not on the edges. Yeah?
But isn't, like, wasn't this one of those ones that you said where it's continuous everywhere is, like,
Everywhere it's defined.
Yeah, so then.
It's only defined on integer. Or it's not on.
So you can't
Okay,
just say,
okay, let's just, taking this little swoop here, right? So for every number from 0 to pi, it's defined. And so for every number, not including 0, not including pi, but every number in between those, it's continuous. It's got a little bit on each side. It never stops.
So you don't just classify those as continuous, you have to say that it's not defined at some places?
There's places where it's not continuous, or discontinuous, as they use in the book. And those places are these integer multiples of pi. Everybody else, everywhere else, it's continuous. Right? How's that match? Oh, yeah, sorry, that's an even number. You don't know what the answer was, do you? No? Okay. That's sad. I'll look for you. Wait, is this my teacher's edition? No. Where's my teacher's edition? Somewhere around here. Oh, you know what? It's at home. I don't even have a teacher's edition. I don't need it. Just well trained. Okay, so there's number 8. Shall we go on to number 20? Is that the next one? So, number 20. By the way, we're not going to get into new lecturing today, by the way.
Oh, drat.
That means we're probably not going to give you any homework, Jim.
Oh, shame.
Oh, maybe I could. All right, let's take a look at number 20. In number 20, we have a piecewise function. It's 3 minus x when x is less than 2. it is 2 when x is equal to 2, and it is x over 2 when x is greater than 2. And they ask us to find out, find each point of discontinuity. Which of the discontinuities are removable, not removable, give reasons for our answers. All right, so when we look, it's so nice to have you back, Maddie. Because you know what, when Edmund does it, it's totally different. Anthony, you probably have to explain what that was about.
She just did.
Oh, she did, okay. All right, so are there any discontinuities when we're less than 2? Is x minus 3 always continuous? It's a linear function. Is there any place where the linear function is not defined or jumps around? No. Okay, how about x over 2? That's another linear function.
That's continuous.
So the only place there's a possible discontinuity is at 2.
But it's continuous then.
Well, let's find out. Let's ask a question that's similar to the one that showed up on your quiz yesterday. What is the limit as x approaches 2 from the negative side of f of x? How do I handle that question for this piecewise definition? I've got to say which one of these definitions is activated as we approach 2 from the negative side. I say it's the first one. And as we approach 2, this expression gives the value 1. When I put 2 into that expression, I get the value 1 back out. What is the limit as x approaches 2 from the positive side? That's actually the question from the quiz. Now this one's is the active function. 2 over 2, it's equal to 1. May I then conclude that the limit as x approaches 2 of f of x is equal to 1?
Yes.
Reason?
Because
Both left and right.
The right-hand limit and the left-hand limit agree.
Agreed.
Exist and agree. Okay? Question. What's f of 2?
2.
Is it continuous?
No.
Continuous means that the limits exist,
On left and right.
left and right hand, and the function has to have the same value. The function's value at 2
Would be
is 2. When x is 2, the function returns a 2. These don't match.
yeah.
We have a discontinuity at 2. Next part. Is it removable? Can we plug it?
yes.
It means if it's removable, it means that we can plug it in. We could plug something in the hole and make it continuous. And that thing we would plug in to make it continuous, we scrap this and we say, well, if the function's value at 2 was 1, the hole would be filled and then we'd have continuity reigning supreme. With jazz hands. So, yes, it's discontinuous. Yes, it's a removable discontinuity because we can plug it on. Any more questions about problem number 20? On to problem number 25. And problem number 25. Give a formula for the extended function that is continuous at the indicated point. So we have f of x is equal to x squared minus 9 over x plus 3. This function is not continuous at x minus 3. Why?
Because it made the denominator zero.
Because it makes the denominator 0. When the denominator is 0, the function's not defined. So what value can we use to plug it in? Answer, well, just like we saw before, it's going to get plugged in with what the limit is of that function as we approach that discontinuity. The limit as x approaches -3 of x squared minus 9. Can I do substitution? No. It's that trombone sound. What happens?
Blows up.
It blows up. So let's algebraically massage it. By the way, my other class thought that was really fun.
I think it's good.
Well, I like the word, I'm going to algebraically massage it as compared to the term that a lot of mathematicians, I'm manipulating it. I don't want to be I don't want to be a manipulator. Okay? So, if we know the factorization of the difference of squares, we know that x squared minus 9 is equal to x minus 3 times x plus 3. These cancel. Now may I use the substitution method? And I get -6. So if I want to plug that discontinuity, if I want to make that removable discontinuity go away, I have to say that f of -3 is equal to -6. That plugs the hole. Are we complete for problem number 25?
Yes.
Great.
So the answer would be y equals x minus 3.
That f of x minus 3 has to equal to 6. Plug the discount. I mean, that's what do they
The
have?
answer to the back book was weird, but that's the answer.
Give the formula for the extended function.
The
Oh,
answer-
Yeah, because
I'm sorry. I would. Okay. Here's what I think the. Blah 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 blah.
Yeah, y equals x minus 3.
Oh. The,
what-
okay. Let me take a step back. I answered the question, what does it take to fill the hole? The truth is that once we do this algebraic manipulation, this function, x minus 3, acts like this function with the hole filled in.
right.
This is the same function as that, except for the filled removable discontinuity. All right. Whew. Is it hot? Is it hot for anyone except me? Because it's boiling. 27. 27. Okay, 27 is, that's 6. Okay, this does not manipulate though, right? But we have that thing. Tell me about that thing, Chris. Help yourself. Get all of that.
X approaches 0, sine of x over x equals 1.
Okay, the limit as x approaches 0 of sine of x over x is equal to 1. Okay, now we're supposed to write the function that extends the function, the thing that extends the function, but since this doesn't have a nice little manipulation, here's the extended version. Are you ready? F of x is equal to the piecewise function where sine of x over x reigns supreme as long as x is not equal to 0 and it's equal to 1 when x equals to 0. Yeah, I know. It's like, that was unsatisfying.
Anticlimactic.
Yeah. It doesn't have a nice clean representation. But we can do any of these in a piecewise fashion and they'd be true. That's 27. 29, if you're okay with that. 29. Okay. 29. We're gonna end on this one. F of x is equal to x minus 4 over the square root of x minus 2, and we're interested in what happens at x equals 4. Okay? The name of this method to massage this function, no, it's not theorem 7. We know we need to find the limit. We are going to use what's called the conjugate trick. I don't think the word trick is official math notation, but here's the idea. This blows up, right? When we put the 4 in there, we get the square root of 4, which is 2. 2 minus 2 is 0. 0's in the denominator. Bad things happen. But watch what happens when I multiply by the conjugate of square root of x minus 2. And its conjugate is the square root of x plus 2. Of course, if I do it on the top, if I do it on the bottom, I have to do it on the top. So what is this? Square root of x times square root of x is x. Square root of x times 2 is 2 root x. Negative 2 times the square root of x is negative square root of x, negative 2 square root of x, and then a negative 4 at the end to finish it off. And the stuff on the top, I'll just leave it just the way it is. Alright? When that happens, these two terms go away, and I'm still sunk.
No, you have x minus 4, then 9 cancel.
Oh, that's right. Those go away. I've got an x minus 4 on the top. I've got an x minus 4 on the bottom. Those cancel, leaving me the limit as x approaches 4 of the square root of x plus 2. And that's over 1 now. Now I can put that in. 4, the square root of 4 is 2. 2 plus 2 is 4. Now, what ends up happening here, if I was just plugging the discontinuity, f of 4 equals 4 would fill the discontinuity. But if we just want to write the extended function, which is continuous and looks exactly like that, this right here, the square root of x plus 2, it ends up being that extended function. So we got through problem number 29. So tomorrow we're going to do lecture 2.4. 2.4 is the last lecture from chapter 2. That means the test is around the corner. How about on Tuesday next? Sounds good. I'm so glad that you agree. All right.